Now we're coming back to something which is in your notes, and the topic is flame wall interaction. I've said yesterday and many times before that since most flames have to be in a box, and since the adiabatic flame temperature of most flames is much larger than the temperature at which the walls can survive, we have to do something about the walls. And knowing how a flame interacts with the wall is a topic which is interestingly not very, very important in the community, academic community, but it's very important in practice. So why do we care? We care because flames, of course, touch walls, and when flames touch walls, you can have a hole in the wall. That's not a good idea. But you will see also that the walls are actually influencing flames quite strongly. One of the simple reasons that you can understand right now is that if the wall is cold, which is normally what it should be, remember we have the exponential minus T over T in almost all reaction rates. So at the wall, the flame cannot burn, normally. So that means that you have to think of this interaction as going both ways. Now, right away, if I tell you that combustion stops at walls, you see that the hydrocarbons, which are able to hide themselves close to the walls or even in crevices, they won't react. They're going to be able to be in a chamber and avoid burning. So these guys, after that, are going to pollute when you release them to the atmosphere. So there is a link also between the presence of the walls and the presence of the pollutants. In the piston engines, for example, we know that the crevices between the cylinder and the piston are actually a source of pollution, which is quite important. Now, another thing that walls are doing, and I will show that in a minute, is that walls are actually also acting on the acoustics of the system. If you have a flat wall, an acoustic wave arriving on this wall, it's not the same thing as having a flat wall with holes, because there the acoustic waves are actually going to be damped by the wall, and it's something we use. For example, in afterburners. Afterburners, you know, are used in fighters, aircraft, to provide more power. So here you have the engine, and here what you do, you inject a lot of kerosene. Again, it's a pretty stupid way to waste kerosene, but you do it. And here you have flame holders. And so you have an additional flame here, and this is what produces these nice pictures you've all seen. You get a big flame coming out of the engine. And if you don't put here liners, which are walls with holes, like this one, they are put on the walls here. When this thing gets crazy, again, it has a thermoacoustic wave oscillation, and the way you damp it is by putting walls with holes there. And you can show that it's a classical, again, classical course in acoustics. They act as damping for the acoustic waves. So altogether, it means that the walls, again, if you're doing an academic study, you don't care about them. If you want to talk about a real flame, you have to care about walls. So I'm going to be talking about the walls of a combustion chamber, but not only in gas turbines. What I'm going to show today is actually applicable to most chambers. Okay, if you talk to, again, I mentioned that before, talk to people in industry, they'll tell you that if you have a combustion chamber, you must burn all the fuel. That's the minimum you can do. You must not pollute too much, and you must not burn walls. So burning all the fuel is easy normally. You just make the chamber longer. At the end of the day, you will burn everything. Okay, that's simple. Doing that without too much pollution is difficult, but doing three is something, of course, you cannot avoid. Okay, if the chamber burns, it can go anywhere, and you don't want to have this kind of problems or this kind of problems. Every time here, of course, you realize that if you have a 2500K flame touching a wall, it's the end of the day for it. So which walls are we really talking about? In a combustion chamber, you have a lot of walls. You have first the plenum walls here. Those walls are cooled. They're cold because the air coming in here is cold. But those walls here, they are really seeing the flame. So those walls have a hard time. And there's a second type of wall, which is actually the wall of the high pressure stator here, because the walls here are actually facing the hot flow coming directly from the engine. So in an engine, you basically have two types of cooling problems. You have the people who have to care about the turbine here, the first stage being the most critical one, the one you need to cool actually. And then you have the people who have to take care of the walls of the combustion chamber itself. And those are not the same technologies. You see here, the first thing you do to protect these veins here is to inject cooling gases. And as I said during the introduction, all the question is to be able to mix them fast enough so that when you reach this wall, you have something which is reasonably warm or cold to avoid having problems here. And then on these walls here, those are very close to the hot zone. And then you cannot do much to help those guys. So what do you do here? You have to use other technologies. And I will show you how this is done. So typically, the design of all the cooling system in an engine is probably the most important things that you can have in practice when you design a chamber first. Let me just say also that during this talk, I will consider that the walls do not burn, should not burn. There are cases where this happens. Normally, if you cool the wall, it should remain cold. If it remains cold, it's not going to burn. To predict that, it means that we are not going to have to compute only the flow, we're going to have also to compute the temperatures within the wall. So again, if I take my CFD hat now, it means that as soon as you talk about wall, it's not only CFD for the flow, it's going to be also a computation for the wall temperature. If the wall cannot remain cold, well, then the wall is going to burn. If the wall is going to burn, then it's going to die after a certain time. But you do that on purpose on certain engines. For example, rocket engines with carbon-carbon technology, the nozzle is designed so that it burns time after time, and then at the end of the propulsion phase, you have lost a lot of mass here. This is not what I want to study here, okay? This is a different problem. Normally, our walls should not burn. So what do you do for these walls here? Well, you have to do something here. The thing which is done in most cases is what we call a fusion. What is a fusion? It's the fact that you're going to drill some small holes here, and through these holes, you're going to have some air flowing into the chamber, and this air is located here, and it's protecting the walls. Now, you shouldn't say that. You realize that in an aircraft, when you're flying, your life depends only on a few millimeters of air flowing on the wall, because if this small film of air goes away, you're dead, okay? The way these holes are drilled really belongs to the secret technology of each manufacturer. This is an example of a turbomeca engine. You see these holes here, each of them. Today when we do CFD, we are meshing each of them. Gives you an idea, there are about 9,000 holes in a chamber like this. And the angle of the holes and the direction of the holes and the shape of the holes makes a big difference. For example, Turbomeca a few years ago changed its technology to drill the hole. You don't do it by hand, okay? You don't have it's a sophisticated system to do that. Huh? A hole looks like this, but because of the way you build it, you use different technology. One of them is such that at the end you end up with a hole which is like that. You have small modifications. So they changed technology a few years ago, and instead of having that, they had a better technology. Better means they had it straight here. Well, the engine did not work. It was burning right away. Because when you do a small change here, as you're going to see in the first simulation, the flow in the hole changes, and it's something else. This is, for example, the flow. This is a DNS, fully 3D here, of the flow in a hole. You see you have separation here. So if this thing is blunt instead of being like this here, you don't have the same flow here. You don't have the same separation here. And remember, this is the velocity field. If I would show temperature, you would see here that this leads to a small film here. And the thickness of this film is what protects the wall. And again, if this film goes away, you're dead. The engine goes away. And it always struck me when I saw that, saying, wow, this is sensitive technology, okay? Just a small mistake here in the holes, and then you lose the engine. It's about the same idea for the high-pressure stator, but the holes are not located at the same place. You put the holes at the places where you think that you're going to have problems. And for the high-pressure stator, you need to compute the temperature in the blades, and I will come back to that in a few minutes. So it's not only a fluid mechanics problem, as I said. You need to compute also the heat transfer within the blade to know exactly where the hot points are going to be. And as I said, there's a coupling with acoustics, which I will not discuss today. That would be a couple of more hours to describe how these things act on combustion instabilities. Okay, everything I've said yesterday about instabilities, you would have to revise it if the walls would be multi-perforated, because it would change, it would add damping. You remember this term I described yesterday? I was talking about P prime, U prime, as the loss of acoustic energy. And I was saying if you have a smooth wall, flat, without holes, U prime is 0. But if you have a wall with holes, this term will not be 0, and you have to redo everything. So I'm not going to do that today. I'm going to talk about flame wall interaction, give you some general ideas, talk about example of coupled LES plus heat transfer simulations that we start doing now. It's really recent stuff here. And then I will also show you example where wall temperatures are actually changing flames also. That it's an ignored factor in many experimental devices actually, that people don't really care about the temperature of the walls, especially when the flame is stabilized. But that's a mistake. We need to care about the temperature very close to the flame holders. And I will not talk about multi-perforated cases because, again, the smooth walls are enough to begin for today. So let me start with general features of flame wall interaction. So you can have 3 types of events. If you are sitting on a wall in a combustion chamber, you can see different things happening to you. The first thing is that if you're lucky, you are just feeling non-reacting gases which are cold, so that's fine. You have a small heat flow, small heat flux. Then suddenly you can be surrounded by burn gases, and that's going to increase the fluxes. But it can be worse than being in burn gases. You can be touched by a flame front which just burns in front of you. So the flame arrives on you, and that's going to generate the highest flux here. So typically, to give you a picture here, that's typically what you have in the backward-facing step flow. If you have a flux detector here, either you are in phase 1 where you just have fresh gases in front of you, and that's cool, no problem. Or you are in phase 2 where you are in the burn gases, or you are in phase 3 here, which is when you are just hit by the flame front. And that's the moment where you're going to have very large heat fluxes. When I mean large, I'm talking about megawatt per square meter. Okay? It's not going to last long. It's going to be hot. You know that the time you remain in the flame is essential. Okay? You just, if you're not sure, if someone has a candle here, you know that you can do that in a candle. You cannot stay. Okay? If you have a high flux on your finger for a short time, it's okay. If you keep your finger on the candle, of course, it's not going to work. So same problem here. It's going to be a problem of heat flux and how long it lasts. So there are, in the literature, a few, again, canonical cases which you can study, which are quite nice, actually. The first one is what we call head-on quenching. Head-on quenching is the very simple case I described already before, except I didn't talk about the flux. You take a wall, you put premix gases in front of it, you ignite the flame moves and hits the wall. You can measure the heat flux here, and this is a classical experiment that you can find in many places. People doing piston engines have studied this problem for a long time. This is 1D, so you can do it rather simply. Then you can have what we call the sidewall quenching. Sidewall quenching is the flame now is propagating in this direction, and you have a wall here. So I will define here what we call the wall distance, which will always be the distance between the wall and the flame front. So here it's this distance, and here it will be this distance. So an example here of head-on quenching computation. So I'm going to play it multiple times. So this is the wall in which we are computing the temperature field, except it's dilated. It's only 10K here, while here it's 1500K. The reason, of course, why the wall temperature is not going up that much is that because the wall is in metal, and it takes a lot of flames to heat up 1 centimeter of metal. Here on the right side here, give me the mouse. Come on. You have different plots here. So you have, let me try to stop this guy. You have the heat release, which is the blue curve. You have the temperature, which is the red curve, and you have the fuel mass fraction, which is the black curve. When the flame is far away from the wall, you basically have a normal flame. Okay? If Moshe would be here, I would tell you that you can write theory for that, and that's true. You have a propagating flame with the standard profiles for fuel going down, temperature going this way, heat release going that way. When you go closer to the flame, closer to the moment where the interaction takes place, at some point the flame starts sensing that something is wrong in front of it. Someone's cold there. So the flame says, well, if something's cold, I may have to decrease my reaction rate, and the flame also sees something else, that there is less fuel left now. And then when the flame comes here, you see the reaction rate starts decreasing, there is less fuel to burn, and then at that point the flame enters a zone which is cold, and because it's cold, there's no way to burn anything now. So there's quenching of the flame dies, and after the flame is dead, you still have, as I said, unburned fuel here. This unburned fuel is not going to stay here indefinitely. It's going to diffuse very slowly, but it's not burning anymore. And of course, the temperature now, you see this point, this high point of temperature is never going to hit the wall. It's not able to go there because it's not burning anymore. And then you have a funny behavior after that. If you track, for example, the point of heat release, now it's going to go backwards and it's going down at the same time. So actually at that point, defining where the flame is kind of difficult. So if you go later in time, you will end up, you see, a little bit of fuel left and a profile of temperature which is now purely diffusive. Okay? And if you wait long enough, you see that in the wall, now of course we are left with a big peak of temperature which diffuses slowly into the wall. So this is an example where the wall temperature does not change much. Of course, if you keep sending flames like this on this wall at 5,000 hertz, after a while the wall is going to feel it. Huh? So when you plot now different quantities, so we're going to plot the distance between the flame and the wall, we're going to plot the total of the heat release, and we're going to plot the heat flux, that means the slope here of the temperature in the wall, versus time. So this is time, this is the flame speed, this is the distance to the wall. So when you are far from the wall, the flame speed is constant. It's okay, it's an adiabatic flame, there's no interaction with the wall. The distance then decreases linearly. The flame is moving like this, constant speed, so distance goes down as a function of time. And the heat flux is zero at the wall, because the wall, for the moment, we are neglecting radiation. The wall sees a flame far away, but it's okay, it's cold for the moment. If there is no radiation, we forget about the radiation for the moment. The wall will start sensing the flame only when the temperature profile will start touching the wall. Then when you go in the interaction, you see the flame stops here. The heat flux goes up at the same moment, and the flame speed goes down at the same moment. Everything's taking place at the same moment. The flame stops, it gives a lot of energy to the wall, and then basically the flame is dead. You've seen, well, Moshe talked about it yesterday, you can do theories for non-adiabatic flames. You can prove actually that when you take a flame and you take out about 1/3 of its power, it's too much usually for the flame, and the flame dies, and that's what's happening here. You are cooling the flame too much, it dies completely, and there is no flame left. Okay? So that's the typical head-on quenching interaction that we see in multiple cases. And then experimentally, you will see that the distance at which the flame stops here is very small, so it's very difficult to measure. What people do in experiments, they measure the flux in the wall, because that's easier to measure. And when they measure the flux in the wall, this is a typical plot. Here you see typically fluxes of the order of 1 megawatt per square meter, which is a huge flux. Okay? Now what you can do, we can do a lot of simulations and measurements, and there's a very interesting and very simple scaling that you can use here. You can plot the maximum flux in the wall. That means we can plot this guy here versus the flame power. Flame power is simply the amount of power that you are producing per square meter of flame. So it's rho Cp delta T, or rho delta H if you prefer, multiplied by the flame speed. This is the amount of energy which is released. And there's a very interesting scaling here, is that for most hydrocarbon flames, it's about 1/3. And again, it's very close to the 1/3 that Moshe discussed yesterday. That means when the flame dies, it releases about 1/3 of its power to the wall, and then it's gone. So if you want to know, if you have a flame in a box, and someone tells you what's the maximum flux I can have on the wall, it's very simple. You compute the flame power, you multiply by 1/3, and you can tell this guy this is how much power you can expect on the wall. And that's a very useful scaling law. There's one exception for hydrogen. Hydrogen is a bit different, but again, it's because hydrogen is so powerful. The ratio seems to be more like 10 to 15%. And we have tested this relation on many cases. It works almost all the time. So that's one you can remember easily. That's an easy way to scale the flux here. The second thing you can do is to look at the minimum distance between the flame and the wall. And you see the flame never touches the wall, and it stops at a distance which we call Y here, YQ for quenching. that you can scale by the flame thickness. Again, remember that this is not a real thickness. Moshe said it also yesterday. That's just an estimate of the flame thickness. The flame is about 3 to 4 times larger. So in practice, that means really that when we say that the PQ here is equal to 3.4, that means the ratio of the distance to the flame thickness. In real world, that means the flame stops approximately at 1 flame thickness of the wall. Again, that's an easy scaling for you. If you compute this number, multiply it by 3.4, you have the distance at which the flame will stop from the wall, of the order of 3.4. So that means a flame will stop at approximately this distance. Now, we talk about sidewall interaction. No, just a minute. Yeah, I forgot to talk about unburned fuel. Okay, if the wall is cold, you will have some hydrocarbon left, and as I said before, this will lead to pollution later. So let's go to sidewall interaction. Now, the flame is propagating in this direction. When you do measurements or simulations of that, you find that this leads to smaller fluxes. Instead of 0.3, you have about 0.15, and to larger minimum flame wall distances. The distance from this point to that point is about 7 times the reference flame thickness. And then this flame can move, no problem. When you do a turbulent flow, you have both sidewall and head-on quenching. For example, here these are different times. You see here the heat release. You see this point is going to hit the wall at a normal angle. So this is initially a head-on quenching. But once it is quenched, this point will move down here. This will be a sidewall quenching. So you can do all kinds of statistics on that, and we did before. But I want to talk here about another interesting case. We see the tube wall quenching. Now, instead of having one wall, you put 2 walls, one on each side. In this case, you see that if the distance between the 2 walls is too small, then the flame will completely quench. And this was discovered about 100 years ago when people tried to compare their flame speeds. They found out that the flame speed they were measuring by propagating flame in a tube were different. So they started asking themselves, why is it different? And so they started changing the size of the tube, and very rapidly they found out that indeed the flame speed in a tube depends on the size of the tube. If the tube is too big, you have instabilities, you will never measure anything. But if the tube is too small, the flame speed goes to 0. And the size of the tube at which you get quenching is typically 50. That means if this duct here is 50 times the flame thickness, the flame cannot go through it. Typical flame thickness being of the order of 0.1 millimeter. That means if you have a tube of a few millimeter wide here, then the flame will stop here. They did measurement of that. That's an old book here by Lewis and von Elber, where they give you the tube diameter which is necessary to stop a flame front. You see it depends on the occurrence ratio. And typically here you have 1 centimeter, 0.2 centimeter. If the flame is fast, of course, then you have to have a smaller tube. Interestingly, this small statement about flame wall interaction is the source of a lot of things. It's probably the source of climate change today. It's the reason why we are sitting in this room, because we are producing all this energy, coming back to the beginning of the century, where people actually use this device to be able to get coal. I will explain that in a few minutes by the example of mine lamps. The other application I want to mention is flashback protection. Flashback protection is this idea that if you use a premix flame located here, you are afraid of seeing this flame flashing back. Exactly what I mentioned for engines. One way to protect the flame, to protect you from flashback, is to have here a grid with holes, with small holes which are actually smaller than the quenching diameter, so that the flame, if the flame hits this wall, it will actually stop there. So this is typically the application which would correspond to that. You've seen it already many times. If you would have a grid here, and the flame would hit it, then flashback would not occur. Okay? And you can actually buy what we call flame arrestor on the market that you can install on your system. And if you're doing a PhD on premix flames, you should buy one. Okay? Now, don't do like me. When I was doing my PhD, I had a nice flame arrestor here. The important thing is that it works only once. Because if the flame flashes back and hits the wall, usually the wall burns. The flame dies, but the wall burns. So you get a big hole then. So the second time, it won't work, okay? So you have to be careful if you're using a flame arrestor, check it's still there after the first flashback. Okay, let me go now to the mine lamp. That's a very interesting story. The guy who found the mine lamps was Davy. He was a lord in England. And this guy took a patent first, then he wrote papers. And the idea basically is the following. He said, if I put a lamp on the head of a guy going into a mine, and if there is gas in the mine, usually it's methane produced, around coal. You don't have only coal, you also have combustible gases. Then this lamp with the flame here, no electricity, okay, at that time. This lamp will ignite the gases, and that will be a big problem. We're going to kill a lot of people. So we need a method to be able to have a lamp here without danger. So the method is simple. You use here a grid with holes, each hole being smaller than 50. This way the light can get out, but not the flame. It's a very smart idea. So the lamp was looking like this. You would ignite here, and there would be light coming out. But if you had surrounding gases which are combustible, the flame would not be able to get out. And that was a major revolution at that time, because that allowed people to go dig into these mines with light and without too many accidents. When I say too many, you're going to see too many still means a lot. Interestingly, I said also that yesterday, if you have an idea, you are sure someone else got the same idea at the same time. Stephenson here, also in England, was not a lord. He had the same idea at the same time. And there was a big fight between these two guys, because Davy was convinced that these guys stole the idea from him, and there was a vicious fight between the two. But actually, I believe that, like always, if you have a good idea, someone else has the same at some point, usually at the same time. So Davy, actually, because he was the Lord, won the fight, it makes sense also. So he got all the credit, but actually it seems like Stephenson got the same idea. So I want to use that to give you an example of what combustion science can do for you. And it's a true story, okay? You're not going to believe it, it's true. So in the 19th century, when you started digging in mines, you dig the coal here, and then you produce usually CH4, some kind of gas like this, methane. When you have a lot of CH4 here in the place where you are digging, and someone else does something stupid, like igniting a spark or something, you get an explosion, okay? And if you get an explosion, you kill a lot of people. And that's, I don't know how many people have been killed in the world. I will give you statistics in a moment, but that's amazing. And people are not aware of that. Even today, you get people killed by thousands every year in mines. So the problem you have here is that if you have gas here, combustible gas, usually you have to stop working. And in the old days, the boss, that was a nice time to be a boss, he said usually it was your fault. The reason why you had methane going out is because you were not digging the coal in the right way. So he would stop paying you, and nothing would work until you pump the gas out. So how can you pump the gas out of this thing? You didn't have pumps anyway. So one solution is to burn it. There are two ways to burn gas in a mine like that, in a mine shaft like that. You can ignite it by accident, in which case you have an explosion. These explosions over the last centuries, have done a lot of people killed, and if you look, especially now in China, you're going to see a lot of people getting killed every year. I've heard numbers between hundreds and thousands. And it's not, this list here is only from 2007 to 2011, okay? If you add the number of people killed by explosions over the last years, it's tens of thousands. So this is a picture of the old days. This is a picture of this is a test actually, of what's happening today. The funny thing about that, I've talked about it also before, is that it starts as a flame and usually goes to detonation. So of course you can imagine what a detonation does in a system like this. I mean, everyone gets killed. So there's a second solution, and that's the smart one. You can burn the methane here slowly. How do you do that? Well, if you wait long enough, you get everyone out of the mine, the light gases are going to go up, and the fresh gases are going to be in the lower part of the mine. In other words, you will have something which looks really much like what we described when we talk about laminar diffusion flames. You will have on one side gaseous fuel, and on the other side you will have air. So you can say, oh, that's a good thing, I could burn them in a diffusion mode. If I can start a diffusion flame, diffusion flame being extremely lazy and slow, if I start a flame here, it will burn very slowly by diffusion, and it will consume all the gas here. there's a small problem. You need to ignite it, okay? You remember we talked about the triple flames, which are needed to go from a mixing state like you have here to a diffusion flame. So how do you ignite it? Well, it's simple. First thing, you take the youngest guy, and then you give him a Davy lamp, and you say you got something to do in the mine, so you don't give him too many details. And, and the guy crawls on the ground. The reason why he needs to crawl is because this is the place where you get the smallest amount of gas, okay? You get air here. And once he's at the place where people know that there is some gas, you tell him to remove the grid from the Davy lamp and just raise your hand, okay? So you raise your hand here. When you reach this zone, where you reach, you know that because you are combustion guys, when you reach the stoichiometric line, combustion will start. So now there are two solutions there. The first solution is that when the guy does that, the fuel and the air were really segregated. You were really in a diffusion mode flame. And in that case, when you reach the point where the guy ignites here, you will have triple flames propagating all over the zone. It will make like a nice sheet of flame, you know, above his head. And if you wait long enough, by diffusion, you will actually consume most of the fuel there. And then you can start working again. That's the good solution. The second solution is that everyone went out too fast. There's a lot of mixing there. And so instead of having a diffusion mode, you're going to have a premixed mode. Now, of course, if you start a premixed flame there, you might go to detonation. Probably the guy will die, but the mine can start operating again. So in both cases, it works. Okay? So, and it's not a joke, okay? People were doing that. It's, I could not believe it. But, so it's an example where you see how you can use combustion science for practical applications here. And of course, you need the Davy lamp, you need the triple flames, you need everything together to understand how this thing is working. So today it's obvious. In those days, it was kind of magical. So let me go back to normal cases now where you have no explosion, and I want to come back to walls and flames. So when you look at the temperature field on a point like this, what you realize very rapidly is that the moments where we have this flame-hole interaction, you have a very large heat flux, but it doesn't last long. So normally, if you're an engineer who cares about the temperature of the wall, you can forget about this phase number 3. What's important is when you are submitted to the burn gases, even if there is no flame. So we can concentrate on that, and that's what I'm going to do now. So here, I just want to remind you of how a jet engine looks like, so that you realize that we're talking about a complex animal here. This is a movie done by CTR, Stanford, where you have here the compressor. Here you have the injection of kerosene. You're going to go into the combustion chamber. You can see here the high pressure stator. That's the guy I'm going to be talking about now. This guy here is going to receive the hot gases coming from the combustion chamber. And since he's the first, he's the one who gets the largest heat fluxes. Okay? So this is really the one where we need to care about the temperature flux, the temperature and the flux. So if you're working for a gas turbine company, if you're working in the turbine department, you are going to be looking at this animal here and wondering, is it going to survive or not? Interestingly, if you want to do that, it seems obvious for us, but it's not obvious for turbine people, that you need to couple the computation of this with the computation of the combustion chamber, because it's really combustion chamber which produces the temperature which is reaching the turbine. It's not clear at all when you go to a company that it's happening this way, because the guys doing the combustion chamber are in one department, and the guys computing the turbine are in another department, and they compete for the same money. So the guys doing the turbine, they keep saying, well, you don't need information for the combustion chambers. We just use 1800K and we'll do the job. Of course, when you look at animations like this one, you see right away that you cannot hope that you can get the temperature right here. In this blade, if you don't know what is the signal, what is the input, especially here, what is the flux. So you need to couple the combustion chamber computation and the turbine computation. When you do that, I will talk about that in a second. You may have to think also about radiation. Yesterday I've started talking about that. You will see that radiation can become important. Coupling now. Coupling is not something which is done usually in laboratories. Normally in laboratories you try not to care too much about coupling, but here you have to. The way it's done in many labs, in many companies, is that basically people would take the mean temperatures and velocity at the outlet of the combustor and give it as inlet temperature for the turbine inlet when they are sophisticated. That's what they do, the maximum they do. That's what we call the weak coupling. The strong coupling would be to couple everything, not only the mean values. Again, you've seen that the mean values anyway are usually not a good idea, but also to couple the perturbations in time. That will be much more difficult. So I will show you some examples of that. Again, you cannot do that if you don't use a very powerful LES solver in which you can compute on a lot of processes. Let me say also that if you do the computation with ones, you can do it today. Okay, a code like Fluent incorporates already today dual computation of heat transfer and flow. The only trick is that they do it with ones, and as always, that's a big limitation. I talked about parallel computing yesterday. If you want to do that now, you have an additional problem is that you need to, if you give you a machine with 10,000 processors, you need to say that the flow is going to be computed on 9,000 maybe, and the heat transfer is going to be coupled on 1,000 processors. You need to make these two codes together on the same machine. So again, in terms of computer science, it's a big problem. The community, the HPC community has been focusing on this problem for the moment. How do we couple one code? How do we parallelize one code? But that's not what we need for industry. For industry, it's not about one code. It's multiple codes on the same machines, all of them working together. That's a big problem for computer science. Okay, let's talk about precision now. Can we forget, for example, about radiation? If you solve a problem like this, you have to ask people in industry, what's the precision you expect? What is the precision you need? You shouldn't ask them, because when they give you the answer, you're afraid of the answer. The answer is, people will tell you, this is a blade, for example, for a gas turbine. If you get the temperature wrong by 25K, it's half lifetime of the engine, which is crazy, because these guys would hope that we will give them the temperature of the skin here with a precision of 25K, which is, as you know, we don't even know the adiabatic flame temperature by 25K. Shouldn't tell them that, but the truth is that 25K is extremely small for a combustion guy. I mean, it's very difficult to imagine that we can do that. Now you have to realize how they do it today. You give them a temperature by 25K and they add 100 to be sure, okay, for safety. But since now more and more they want to reduce the safety margins, they start wondering, are you really giving us 25K? And if you don't give the 25K, this is what happens, okay? You're losing pieces of the blades, which is not good. So I'm going to show you a computation here of, again, one of these turbomeca engines where we coupled all these things. This is the geometry which you've seen before, air inlet, kerosene, outlet, and we're going to be looking at this guy here, which is the high pressure stator, which is the most difficult place in the engine in terms of temperature and lifetime. So if you do that, you're going to have to couple now not 2 but 3 codes. You're going to have to couple a code for LES in the fluid with combustion. Then you need to compute the temperature within the blade, and you have another code to do that. And you need a third code to compute radiation. Since we talk about 25K, which is a very small number, it's a logical point to say maybe we need to add radiation there. If you want to be precise by 25K, probably it's a good idea. Now, it's not only 2 codes you need to couple, you need 3 codes. If some of you have to do that, I recommend you take a look at this code here called OpenPalm. It's an open source coupling tool which does this job for you of taking 3 or 4 codes and running all of them together on a parallel machine. Believe me, if you need to do it on your own, you should start with a code like this instead of trying to do it on your own. For example, you could have a stupid idea to say that this is going to be a subroutine of that code, and this is going to be a subroutine of that code, and trying to merge them. Believe me, it's not going to work. It's much better to leave them run independently and couple them with a strategy like that one. But again, we're talking here about computer science. It's not really what I wanted to do today, so I'm going to jump to the results. So this is typically what you find when you compute the temperature in this system in an uncoupled way. And the high pressure stator here is impinged by the hot zone. This is the temperature field. You can see how these hot points are impinging on the blade. I'm going to show you two simulations. One of them is, I'm going to call it the two-code simulation. We're going only to couple the combustion and the conduction in the high pressure stator. And in the next one, the three-code simulation, I will add radiation to see what the difference is. I will not give you the details of the inside cooling of the blade. This is not the blade we use. All these things are secret. This is the kind of technology which is crucial, so we will not see the real blade. The blade inside has a very funny pattern for cooling. So we will replace the real blade by a blade in which we say inside the blade we have a convection coefficient and a cooling temperature which is imposed on all this surface here. On the other side of the blade we will explicitly compute the heat transfer and the flow using a law of the wall which I described yesterday. Now if you look at the blade itself and at its temperature, you have to wait, this is versus time, you have to wait a certain time until all temperatures in the blade, the mean temperature, the max temperature, and the minimum temperature get stabilized. This happens after a certain while, a certain iteration procedure that I don't want to describe here. You can see here the temperature in the blade changing versus time, and at some point the temperature in the blade gets stabilized. So let's talk about radiation now. You know, radiation really is produced in the very hot places in this flow. It goes like T to the power 4s. So here, there will be no radiation almost. All the radiation will be produced by the zone here. For the high pressure stator in this engine, it's not general. The high pressure stator does not see this zone, and light doesn't take turns, okay? So there is no way this point here can be influenced by direct radiation from this point. So what we call the direct effect is almost zero here. The indirect effect, however, is not zero, because if you have radiation here, this is going to change the temperature profile here. And since this is flowing to the high pressure stator, there will be an effect of radiation here, which will be an indirect effect. You compute here this is the radiation source term. So this is really where heat is going away due to radiation effects, and you see it's about 5% of the total heat release, which you lose again because of radiation. It's not much because this is not a sooting flame. You know, it's a flame which is blue, and the radiation level is not that much, but still, it would mean 50K less on average for outlet temperatures here, which is a lot compared to the 25K these guys are expecting from us. So we computed the radiation fluxes on the walls. This is the radiation fluxes on the wall, and as expected, the radiation flux, the direct radiation flux is zero on the high pressure stator. It's not zero on the walls of the chamber here, but that's an indirect effect, and that's the one we're going to measure now. This is the result you obtain now when you plot the temperature in the blade starting from this point here, 1, 2, 3, 4, 5, etc., going back. These are the points which are indicated here, 1, 2, 3, 4, 5. And so you see that the temperature in the blade, again, we cannot give numbers, that's about 200K here. And you see the computation without radiation, the computation with radiation. And you see that radiation does things that are not intuitive. It's not always by saying that radiation will decrease the temperatures. On the skin here of the blade, at some point you get, with radiation, lower temperature, but at other points you get higher temperatures, just because things have mixed differently in the primary zone of the combustion chamber. So it means that if you want to have a precision of 25K, you have to add radiation. That's a pain again, because radiation, as I said, is very expensive. Okay, this is not the only issue here. We talk about flame wall interaction. I want to finish by showing the effect not only of the flame on the walls, but showing the effect of the walls on the flame. And I want to do that again in the framework of combustion instabilities, because this is what we discussed yesterday. So we've seen that walls change the dynamics of the flame, and actually, again, if you're doing an experiment, you probably know that when you start your experiment, you have a certain flame. If you wait a certain time and the temperature gets up, at some point you might have another flame. And so we know from simulations and from experiments that there are flames which are very sensitive to the temperature of the walls. One example again is this one. It's easy here to see that this point here, which is very hot, if you cool it by adding any cooling system, it's going to change the flame stabilization. So there are points in the flame which are extremely sensitive to temperature modifications. Typically the points where you anchor the flame. All the points where you stabilize the flame are very important. If you cool them or if you heat them, you're going to have a different result. So the link now between the heat transfer, so the walls, and the instability is an open issue. We don't really know if it's important or not. A lot of people probably in this room are doing experiments on flames, and if I ask them what is the temperature of the walls, they will tell me, I don't know, I just know they don't burn. But it could be between 100K and 500K, I have no idea. So let me give you an example here of a setup that we do in Toulouse. It's a very simple flame. You have a flow here which is laminarized going through a convergent nozzle, and at the end here we have a big slot where we have a flame stabilized on it, which has this shape here, and we're going to look at this flame from the side to see its shape. We're going to look here at the temperature of the walls, because we're going to cool these walls on purpose. We can control the temperature of the walls, and to do that we use an infrared camera. And we also cool the walls here by adding water going through the walls, because we want to monitor the temperature. So we're going to be looking at the flame movement, looking at the temperature of the wall, and looking also at the emission here. And the cooling system is such that we can either switch it in, switch it off. Okay, so this is what you're going to see in the movie here. This is a direct view of the flame. The flow is premixed entering the system like this, so it's a classical Bunsen flame. Here, the tomography picture is the picture of the side here of the wall. And here you have the fluctuation of heat release. That means this measures really the instabilities. And you will see that when we start the flame, this will be time here. It will be speeded up after a while because it takes too long. Initially, the flame will be unstable. Then the walls will get warmer. The instability will go down. And then we'll start the cooling system, and you will see the instability will go up because the walls will be, again, cooler. So let me just get this thing working, if it wants. Then we ignite the flame here. I think you understand it's noisy. So for the moment, these walls are cool. Now we're going faster 40 times. And you can see that when the walls are heating, the intensity of the fluctuation is going down. Actually, at the end here, the wall will be very warm, the flame will be almost stable. You don't see any modification now. It's almost stable here. And now we start the cooling again. So we are cooling the walls, so you can see temperature going down again. And you see the fluctuations are going up again, you see the flame fluctuating again. So it really proves that in a system like this, there is a direct link between wall temperature and instability. And okay, now it will be almost back to the initial state, okay? And again, in multiple models for thermoacoustics, people don't even care about the temperature of the wall. It's not a parameter that is in your model. So this shows that it has to be there. You can plot actually the pressure level as a function of time, which means actually as a function of temperature. And when you start the cooling back, you see that it's going unstable again. So we studied this phenomenon on a simpler flame, not that one, another one, which is indicated here. This is a multiple hole flame. So every time here you are injecting gases, and we are going to pulsate this flame to look at the flame transfer function. Again, I've shown that yesterday. If you want to study the stability of a flame, it's a good idea to start by looking at the response of this flame to acoustic excitations. So we're going to pulsate flames, and we're going to see how the pulsation is changed when we change the temperature here of the flame holder. So I'm not going to re-describe again what the combustion instabilities are. You have seen that yesterday. You have seen also what the principle is for flame transfer function. We are going to send acoustic waves there and look at the response of the flame. One of the things which must be said about this business is that we need to talk a little bit about quantification of uncertainties. When you plot diagrams like this one, which is a typical diagram for combustion instabilities, you end up saying that you have a domain where when the time delay is such that it's between 0 and this value, it's safe. That means you are stable. And if it's between this value and this value, it's dangerous. So you go to industry again, and the guys tell you, well, okay, where is my time delay now? Time delay is here for your burner. And the guy says, are you sure it's here? Could it be here? And you tell him, well, I don't know. I don't know actually how uncertain my prediction is. And it's very important to be able to quantify now in this system the exact uncertainty that you have on your prediction, because of course it's a 0 or 1 problem here. Either it's stable or it's unstable. So if you say it's stable and it's unstable, then you're in bad shape. So it's important to quantify not only the delay, but to know the precision of the prediction. That's also a very new field. Quantification of uncertainties is only arriving in the field of combustion, but I'm sure that you will have to face that in the years to come, because people now don't want an answer. They want an answer and a safety margin. Like you listen to the weather, they tell you tomorrow it's going to be nice, and the confidence index is 3, 4, or 5, or something like this. You want to know that before you make a decision on your weekend. So we're going to look at two flames, which are both laminar. One of the reasons why we came back to laminar flames is that we were computing turbulent flames, and as always, turbulent flames are so complicated that if it doesn't work, you don't know why. So we went back to laminar flames. One of them is a flame coming from École Centrale. The other one is the flame of Kornilov. And in both cases, you have measurements, and you will see actually that the temperature of the flame holder plays a big role. So this is the flame of Boudy here. So you have 49 small holes on the plate. So 49 small flames like this. And the flame of Kornilov is only 8 premixed flames located like this. And they are both laminar, and we are pulsating them. So the first thing you do is to compute the mean flame. So you have here the mean. This is DNS. This is the DNS computation. This is the experiment. You see the mean flames are very close. Same thing for Kornilov. The thing you see also for a flame like that, and this one is the same, is that these flames don't touch the wall. There's always a distance here between the foot of the flame and the wall, because the wall is cold, not always at the same temperature, but cold enough so that the flame cannot go there. It's easy to see why. If the flame would go here, the temperature here would be 2000 K. The wall would be gone. Okay? So there's always a difference between the place where the flame starts and the plane here of injection of the gases. And this zone is important. People have tried to ignore it for a long time, but it's important. I'm going to show you in simulation here for the Boudy case, this case, where we're going to have two cases. One of them will have a cold wall here, and the other one will have an adiabatic wall. An adiabatic wall. So the adiabatic wall is on the left here, and you see the flame here starts right away at the bottom here of the injection, and here the wall is cold. And we are pulsating these passages. And you see that when you're pulsating the adiabatic case, well, you have one response, and when you're pulsating the other one, you have another one, because here the foot of the flame is moving also up and down. And the response of these two flames are quite different, which tells you that if you want to measure a flame transfer function here, you need to care about the temperature at the foot of this flame. You cannot ignore that. You cannot say, I don't care about the temperature. You have to worry about that. Then, of course, you can match. This is the phase of the flame transfer function. That's what I keep saying, to my students. If this is typically the experimental results, the lines, and the symbols are the DNS. Normally, it's always possible to match, because you have enough free parameters in your DNS, and this is what we did. And what this shows only is that you have enough free parameters, for example, the temperature here at the base of the flame, to recover what you see in the experiment. But if you would like to predict it, then you would be in trouble. So what we did is a first-order quantification of uncertainty on this system to see what's important in this system. For example, when you do DNS like this, you have some free parameters that the PhD student knows about and the advisor tries to ignore. Is that you need to fix a temperature here for this wall, you need to fix a temperature here for that, you need to choose a flame speed, and you need also to choose an inlet temperature. And here I won't talk about flow expansion, but it's the same problem. All these parameters are more or less free. And what the PhD student is doing is that he's tuning all of them until he gets the result that the advisor likes, basically this curve, okay? It's not something we should do, okay? It's a bad idea. So what we did is to try to be honest about it, and we did a sensitivity analysis. How do you do a sensitivity analysis? Where you take one flame speed, you multiply it by 1.1, by 0.9, you redo the simulation, and you look at the sensitivity of the results. This is a map of the sensitivity of the results, and you see that the results in terms of flame transfer delay tau are very sensitive to certain parameters and less sensitive to others. So I'm not going to go into all the details here. This is a summary of the results. Basically, this is the sensitivity. You see you have very large sensitivity to the flame speed. That's the first order parameter. And you have a very large sensitivity to the temperature here of this duct. That means if you get this temperature wound, you get the flame transfer function wound. And the other parameters are less important. So that really means that if you're doing a computation of this system, you have to worry about temperature here and there, about flame speed. The temperature of the air here is not going to be a problem, and the angle of expansion is not. So that really means you can forget a lot of things, but you have to care about these things to do this computation right. And of course, these things control the result. So you can, if you don't know them, you can adjust them to find the right result. But it's not honest. The honest thing to do is to try to find them. The problem is that finding them, if you want the model for the flame speed, you need to have good kinetics. And we are back to step one, which is we don't know the kinetics to the level where we can say this is the flame speed with a precision of 1%. We just cannot do that. So we have a problem. And if you want to have the wall temperature here, you need to compute the temperature of the walls, which we didn't do at that point. So that means you really need to couple your computation of the flow with the computation of the wall. It's a bad conclusion for people doing PhDs, in labs, because it means you cannot just do a simple code to compute the flame and expect that you're going to have reasonable results. You're going to be able to tune them, that's for sure. But if you want to predict, for example, typically, if you want to work in a blind test mode, I give you the geometry, I don't give you the results, you do the computation, come back to me in 6 months, and I will tell you what you should have found, then you'll be in trouble. You're not doing a predictive computation. So that's really an important thing is going to develop in the future. It's also a discussion we had yesterday with the other teachers here, that there's this trend when you write a paper that more and more, if the experimental results don't match the simulation, you don't want to publish them, or you're afraid that you're going to be not refused when you publish results. I think it has to change. People have to be able to produce results saying it does not work. I didn't tune anything, it does not work. Maybe I could have tuned a lot of things and made it work, but it's not the idea. The idea is that we should really show results honestly, and if they don't work, it's fine. Of course, it's difficult to have a paper accepted when the conclusion is it doesn't work. But I think we have to change the way we do that, because the funny thing today is that it's always working. You read all the papers at the end, the guy says it's working. But then you apply it to another case and it's not working anymore, and we all know that. So we should be more honest in the way we handle papers. So to conclude on this wall temperature business, so the interaction between the flames and the wall cannot be ignored. You can compute it. It's a little bit difficult. You need to couple codes. And it's changing a lot of things. And probably you should think about this kind of dual heat transfer flame simulations if you're looking at problems like this one. Okay, I think we're able to take a break. Is there any question before the last talk for me? No? Okay, one more coffee and then be back at in 15 minutes.